Today we're going to do a lab on the Lorentz Force. Basically, we're going to put a beam of charged particles, well, charged electrons to be precise, in a magnetic field. And we know the Lorentz Force, F equals QVB sine theta, there'll be a force causing them to move in a circle. We're going to send the electrons going that way and put a magnetic field going either this way or this way, depending on how we set it. Now, what we're going to do with this is we are going to measure something that the elementary charge to mass ratio, which is E over M. It's the charge of an electron over the mass of an electron, with the negative sign canceled out. Now, just to show you how this goes, I'm going to start by giving this a deflecting voltage. Oh, sorry, an accelerating voltage. This accelerating voltage, what it does is it is going to do exactly as it says. It's going to accelerate some electrons. Right now it's at 150 volts, and you can see I get this electron beam. As I play with this, I can get it brighter or dimmer, but if I make it too bright, it comes hard to use. And that's just a beam of electrons. Right now, there is no magnetic field. What I'm going to do is I'm going to make a clockwise magnetic field. And I'll zoom back out so you can see what I'm clicking. That means the magnetic field going clockwise. I think the light would go the other way, is going clockwise. But the magnetic field is going, well, that's not the magnetic field. It's the current for it is going clockwise. So that means the magnetic field is into the thing. Now, QV cross B, right? We have V, and I'm saying it's into the thing, but keep in mind the charge of electron is negative, so that's going to flip it. So that's going to go and give a force going upwards. So let's start giving it some value. We're going to right now, how are we doing, sorry, I should say this actually. How are we doing the magnetic field is these big rings around. They're basically electromagnets. It's just a coil of wire. So what I'm going to do is I'm going to control the current I put in there. And I'm going to start by giving it the minimum current required to make a complete circle. And so as I up it, you can see right about here, I have a nice complete circle. That current corresponds to 0.8 amps. Now what I'm going to do at that current is I'm going to figure out the diameter of this circle. Now this is one of the least precise things I think we do in this class. But how I'm going to do that is I'm going to slide this guy around and get it so that it's even with the edge. And it's hard to tell with the video. I can see if I zoom in if I can get it. But this guy has a kind of a teeth shape. And so when you're straight on it, they look lined up. And I'm going to, like if I look at an angle, you can kind of tell if we're straight down it. And I'm going to get this thing so it's lined up with the left side of the circle. And I'm going to record what that value is, which as you can see is 4.6 centimeters. I'm then going to go, give me a bit of resistance. And I'll try to line it up with the right side, which is right about there, about 16. So I said 4.5 and 16. Using that, subtracting, we can get the diameter of the circle. And using the diameter, we can then take the diameter and square it, and then we can start going and doing all the calculations. I'm then going to repeat this for a series of other currents, and I'm going to find 4 different current values, where I'm just going to go and kind of up the current more, and then find the diameter here, and then find the diameter here, and then find the diameter here. I'm not going to make you watch me figuring out the diameter of each one of those, but I will give you that data.